This video is over section 12.2, algebraic properties of limits. In this section, we're going to dive a little bit deeper into limits and how to find limits algebraically. So we will use different laws or properties of limits and find limits of piecewise functions given the function rather than the graph, and also determine points of discontinuity given a graph. On the first several slides, we just have basic properties of limits, and take some time to look them over, but they are pretty basic. One thing here, b is just a constant, so anytime you want to find the limit of a constant, the result is a constant. For example, if b is equal to 3, for example, all that means is the function itself is equal to 3, or y equals 3. We should know that the equation y equals 3 is just this line. So it does not matter what x value we are approaching. If it's this one, this one, this one, this one, it doesn't matter. No matter what, the intended height is 3, so the limit is 3. That's all this is saying. The limit of a constant is a constant. These other properties are basically direct substitution. Anywhere you see an x, you plug in this value. Some more properties, basically the distributive property holds. Again, b is a constant, so the limit of a constant is a constant, so you can simply move that out in front. And then just find the limit of this function. Here, you'll find the limit of this function and either add it or subtract it to the limit of this function. Here, you will take the limit of this function and multiply it by the limit of that function. Here are the last properties. So just take a few moments and look through some of these, and I'm going to show you how to use some of them. So here we have two examples, and this first one we want to find the limit of this polynomial. So what we'll do is we will just take the limit of each of these separately. So first, this is equal to then the limit as x approaches 5 of x squared plus the limit as x approaches 5 of 3x minus, because we have a subtraction sign here, the limit of 1 as x approaches 5. Then we will evaluate each of these limits. Here, I'm simply going to plug in 5 right here, so this is 5 squared. When I plug in 5 here, this is 3 times 5. I have nowhere to plug this in. This is an example of finding the limit of a constant. The limit of a constant is that constant, so this is minus 1. This gives me 25 plus 15 minus 1 results in a limit of 39. So this limit is equal to 39. This example over here can be rewritten in the following way. I can take the square root of the limit as x approaches -2 of this function. So, evaluating this limit the same way we did in the previous problem, this becomes the square root of the limit as x approaches -2 of 5x plus the limit as x approaches -2 of 19. All of this under the radical. So, when I evaluate this, I plug in -2. And when I evaluate this, it's a constant, so I just have 19. So this is the square root of -10 plus 19, which results in the square root of 9, or 3. So this limit is equal to 3. The intended height of this function as x approaches -2 is equal to 3. This here just talks a little bit more about limit properties and using direct substitution. Direct substitution is nice when dealing with trig functions. And so we're just going to do a couple more examples of direct substitution. So here we want to find these limits. So now at this point we don't have to write out the limit of this minus the limit of this, because we are big kids now and we can see that all we need to do is plug this in. So this limit is equal to -5 cubed minus 8. When we evaluate this, we have -125 minus 8, which is equal to a -133. Not so bad. Go ahead and pause this and try to do number 4 and 5 on your own. In number 4, I have two x values that I need to plug 8 into. So I have the square root of 8 minus 2 divided by 2 times 8. This gives me the square root of 6 divided by 16. These have a 2 in common. 2 goes into 6 3 times and into 16. Oops, 8 times. I'm sorry. So this radical becomes, and I'm just going to write this as the square root of 3 over the square root of 8. Remember, we can break this down into the square root of 4 times the square root of 2, or 2 root 2. So we have the square root of 3 over 2 root 2, rationalizing the denominator. We have the square root of 6 divided by 2 times 2, which is 4. So this would be the final answer. Okay, well, using direct substitution in this trig problem, we would have sine of pi over 3 minus cosine of pi over 3. We should know that the corresponding ordered pair for pi over 3 is 1/2 root 3 over 2. Remember, the x value is cosine, the y value is sine, so we will have the square root of 3 over 2 minus 1/2, and you can write this as a single fraction over 2, the square root of 3 minus 1. So this is using direct substitution. Now, of course, direct substitution is not always going to work for us. In fact, sometimes direct substitution will give us a result like 0 over 0. Well, what is 0 over 0? Is it 1? Is it undefined? Is it 0? Who knows? That is a mathematical debate that has been going on and on and on. Therefore, we refer to this as an indeterminate form. And there are actually lots of different indeterminate forms, and some of them are written here. Anytime we use direct substitution that produces an indeterminate form, we, by using direct substitution, we have to use another method of solving. So if you use direct substitution and you get one of these indeterminate forms, you have to try another approach. Oftentimes, factoring or multiplying by the conjugate will allow us to simplify the function so that we can then use direct substitution. I'll show you some examples. Looking at this, if I were to plug in 5 into this function, You know, the top's going to, take a little bit of work, but I can see if I just plug in 5 here, I get 0 in the denominator, which I should know right away is a faux pas and something that I don't want. So I know that direct substitution's not going to work. So what I need to do instead is I need to look at this and I want to factor it. Okay, in looking at this, I have 4 terms, so I'm going to factor this by grouping. So if you have forgotten how to factor by grouping, make sure you're paying attention. I'm going to group the first 2 terms and the second 2 terms. I'm going to do this right down here. And what I'm going to do is I'm going to take the GCF out of each group. So looking at the first group, my greatest common factor is 4x squared. If I factor out a 4x squared, then I am left with x minus 5. I'm going to do the same thing with the next factor. Looking at these 2 terms, I'm going to factor out a negative 9. And then I'm left with x minus 5, because a negative times a negative is positive. Now remember, when you factor by grouping, these 2 factors need to be the same. If they're the same, you have done things correctly so far. If they are not the same, go back because you have not factored correctly. When those are equal, take it out. That becomes one of your factors. And then the remaining pieces, your GCFs, become the other factor. Now, I know this is a difference of 2 squares, and this can be factored further, but you don't need to in this particular case. If you want to, go for it. Okay, so the reason I'm not going to factor anything further is I'll show you why. So limit as x approaches 5. I continue to write this piece until I plug in that x value of 5. You have to write this until you evaluate the limit. That's very important. We have factored the numerator to get this. And our denominator is x minus 5. Well, these factors cancel out, so I am left with the limit as x approaches 5 of this. Well, if you look at this, now we can use direct substitution because nothing is weird. So when I plug this in, I'm now evaluating the limit, so I don't need to write this anymore. I have 4 times 5 squared minus 9. This is 4 times 25 minus 9. 100 minus 9 is 91. So the intended height of this function as x approaches 5 is 91. Okay, here is another example. Now, this one's a little bit easier to evaluate in your head. If you attempt to use direct substitution and you plug 1 in here and here, you end up getting 0 over 0, which is in fact an indeterminate form. So you cannot use direct substitution and you are forced to use some other method of solving. The method of solving is to multiply by the conjugate of this. Remember, the conjugate is the exact same thing, except you change the sign in between the 2 terms. Whatever you do to the top, you must also do to the bottom. So we are going to multiply this function by the conjugate. So this limit becomes the following. This gives me the quantity 3 plus x. This and this cancel out, and then I have minus 4. In the bottom, I could go ahead and FOIL this all out, but I'm just going to leave this as is for now. When you are writing it, make sure that the square root is only over the 3 plus x. Okay, moving on, I'm going to continue to simplify that numerator there. And that ends up becoming it becomes x minus 1. Well, what do you know? We have an x minus 1 in the denominator also. So these x minus 1's cancel. Well, when they do, now we have the following. And we want to see if we are able to use direct substitution. I don't end up with 0 in the denominator or an indeterminate form. In fact, when I plug 1 in, I get the following. So I know direct substitution will work. And this limit is equal to 1/4. Let's look at another example. Wowee! Here we have fractions within fractions. So let's clean this up a little bit, all right? You know, and I can't plug in 2, all right? That will give me an indeterminate form. Okay, so let's clean this up. I want to get rid of these fractions in the denominator, so I'm going to multiply by the LCD, the least common denominator. Looking at this, my least common denominator is 2x. And whatever I do to the bottom, I must do to the top. So I'm going to multiply everything by 2x. That gives me the limit of, and the top I'm just going to write this as 2x times the quantity x minus 2. And in the bottom, when I distribute this, I have 2x times 1 over x. That results in 2 minus 1/2 times 2x gives me x. All right. Well, looking at this, I want to try to cancel things out because here I still cannot use direct substitution. Well, I notice that I have an x minus 2 and a 2 minus x. So these are really close. In fact, they only differ by a negative. So what I'm going to do is I'm going to factor out -1 here. So in the top, if I take out a -1, the signs change from each of these. So this will be a 2 minus x, which is what we have here. So now these cancel, and I'm left with the limit as x approaches 2 of -2x. And now I can use direct substitution to get my final result. When we were looking at graphs of functions, I said many times as we approach some x value from the left and from the right. Well, there's specific notation for that, and that's given to you on this slide. If we look at this notation here, we have something slightly different. And it looks kind of like an exponent, and it's a minus sign. If we see that, that means the limit as we approach C from the left. So the minus sign is approaching the x value from the left. On the other hand, if we look at this, now my little exponent looks like a plus sign. That means approaching C from the right. Remember, if I have a function, the limit from the left needs to be equal to the limit from the right. if they do not have the same intended height, then the limit does not exist. Here's an example. Here, this is the function f of x, and this illustrates the limit of the function as x approaches 2 from the right. This intended height is 4. On the other hand, as we approach 2 from the left, this intended height is 3. Since these values are not equal, the limit does not exist. And notice here that we don't have a symbol next to this 2. That means just the limit itself. So the limit does not exist because the left-hand limit does not equal the right-hand limit. In order for the limit to exist, those two must be equal. Here's a function, and I have it graphed for you on the right. If I look at this, typically I'll want to illustrate that the limit as x approaches 4 from the left, and I'm just going to call this f of x, all right, just so I don't have to write it out again. The limit as x approaches 4 from the left. Okay, here's the x value of 4. As I approach it from the left, the intended height of this function is -1. On the other hand, as I approach 4 from the right, so as I'm approaching this x value of 4 from the right, this intended height is a +1. Since the left-hand limit and the right-hand limit are not the same, we can say that the limit as x approaches 4 of f of x, or in this case, this does not exist. Here's the last type of example that you will see in this section. You'll be given a piecewise function, and you'll want to evaluate each of these limits. Now, some students are very visual, and they will want to actually graph this out. And you can do that, but it's going to be very time-consuming. And I'm going to show you how you can solve this without having to graph it. There are some key items to look at. Some of the key items that I want you to notice is that something fishy is going to be happening at an x value of 1, and something fishy is going to be happening at an x value of 3. So those are some x values that we're going to want to analyze, and as you can see, all of our examples are dealing with those x values. Okay, let's look at part A. In part A, I am interested in the function as x approaches 1 from the left. Well, if I'm approaching an x value of 1 from the left, I'm analyzing x values less than 1. So that means we are going to look at x values less than 1. Well, x values are less than 1 in this first piece here. So really, when I am going to evaluate this, I'm going to specifically look at the first piece. I can use direct substitution here, and when I use direct substitution, I just plug in 1. Okay, this just tells me which direction we're heading from, nothing more. So when I evaluate this, I have 3 times 1 minus 2, which gives me 1. So this limit is equal to 1. Now I'm going to evaluate the limit as x approaches 1 from the right. So looking at this chart here, as x approaches 1 from the right, all of these values are bigger than 1. So this means we are looking at x values greater than 1. According to my information, x values greater than 1 deal with this second piece in my piecewise function. So I'm going to be analyzing the limit as x approaches 1 of x squared. Once again, I can use direct substitution. This symbol doesn't mean anything at this point, so I'm going to plug in 1, and I have a limit of 1. So we have evaluated the left-hand limit and the right-hand limit. So now we want to put these together to see what this limit is. So the left-hand limit and the right-hand limit are the same, which means the limit exists and that limit is equal to 1. Let's see if we're just as lucky looking at this next set of problems. Okay, now I want to approach 3 from the left. If I'm approaching 3 from the left, these x values are less than 3. X values are less than 3 in this second piece, so I want to evaluate the limit as x approaches 3 from the left of the middle piece, which is x squared. I can use direct substitution, so I want to evaluate 3 squared, and that is equal to 9. Evaluating the function as x approaches 3 from the right, these x values are greater than 3. So I'm going to use the last piece, and I'm going to evaluate the limit as x approaches 3 of 2x. Using direct substitution, I have 2 times 3, which is 6. So I found the left-hand and right-hand limits. So now to evaluate the limit itself, since these are not equal, this limit does not exist. I stole this graph from the last lesson, but we're going to do the same thing. So pause this and see if you can come up with the correct answer. The left-hand limit as x approaches 2, the intended height is 1. The right-hand limit is 2. Because these are unequal, this limit does not exist. That concludes this lesson.